So again, the prior belief is the just information before the data is observed. Okay, so you must have your own belief or guess, or you must have your own information before the outcomes are observed, right? Because you have so much experience about flipping coins, and also you might have learned of some theory about the coin toss like this, right? So then also you might have read some literatures about flipping coins. Okay, so then just for example, suppose your frame information is roughly theta should be between 0.2 and 8. Your guess is theta is 0.5. Okay, 0.5, but it could be 0.6, 7, or 8, or 0.2 or 0.3 like this. Okay, right? So then how to specify our prior belief using any particular any distribution. And one popular distribution for this such variable between 0 and 1 is beta distribution. Beta distribution is defined by these two parameters, alpha 0 and beta 0. And this is the density function of the beta distribution. And this is gamma function, which is not important at all. Just this is sort of the function, okay? And this is function of alpha 0 and beta 0. The point is that alpha 0 and beta 0 are chosen by yourself, okay? So alpha 0 and beta 0 are not random variable because this is your choice. So these are non-random variable. These are just numbers, and alpha 0 and beta 0 are numbers. Then the gamma of alpha 0 and beta 0 are number 2. But we don't know what it is. You don't need to know either. And this is Cornell. Okay, theta to the alpha 0 minus 1, 1 minus theta to the beta 0 minus 1. So this is density function of the beta distribution. And once alpha 0 and beta 0 are given, then this is expectation. This is expectation, alpha 0 over alpha 0 plus beta 0. And this is variance, alpha 0 times beta 0 divided by alpha 0 plus beta 0 square times alpha 0 plus beta 0 plus 1. Okay? And then one thing you need to know about the beta distribution is that suppose alpha 0 and beta 0 are both 5. Okay? Both 5. So then 5 over 5 plus 5. So then what? Expectation is 1/2. 1/2. And then there must be some the variance. And you see that here this is square term. So how many alphas here? Here alpha here must be alpha square and beta square, and these are another alpha 0 and beta 0. So then in this denominator, so then you see that there are alpha 0 to the 3 and beta 0 to the 3, right? So then when you compare alpha 0 and beta 0 are both 5, and the case the alpha 0 and beta 0 are both, say, 500, okay? Alpha 0 and beta 0 are both 500, then still the expectation of theta must be 0.5. So in terms of the expectation, these two cases are the same. Alpha 0 equals beta 0 equals 5, and alpha 0 equals beta 0 equals 500. But if the scale of the alpha 0 and beta 0 is very large, then what happens to variance? Variance will be much smaller. Okay? So then if the alpha 0 and beta 0 are both very large, then variance are very small. That means this distribution will be very tight, right? And or the density function must be very sharp. But if alpha 0 and beta 0 are both very low, if small numbers, then this density must be very spread. Okay, it must have very large tails, right? So this is some features of the beta distribution. Okay, so alpha 0 is not a mean, and beta 0 is not a variance. Okay, so mean and variance are determined by alpha 0 and beta 0 both. Okay. And suppose alpha 0 and beta 0 5, because I believe that theta must be between, it's not necessary, but roughly I would say with the probability of 90% or 95%, I strongly believe that theta must be between 0.2 and 0.8. Of course, it could be 0.1 and 0.9, but such probability is very low. But roughly, I would say with 90% probability, I believe that theta must be between 0.2 and 0.8. And then that means mean is 0.5 and 2 standard deviation is 0.3, right? Mean is 0.5, and I believe that mean is 0.5 and the 2 standard deviation is 0.3. And 0.5 mean and 0.32 standard deviation correspond to alpha 0 and beta 0 are both 5, right? So if alpha 0 and beta 0 are both 5, that means mean is 0.5 and standard deviation is 0.15. So that means 2 standard deviation is 0.3. So the 90% confidence band or credibility interval is 0.2 to 0.8, right? So this alpha 0 and beta 0 correspond to our prior belief. Okay. Then our goal is to estimate the theta, and theta is random variable. So what does it mean by estimating the random variable? It means that we estimate its distribution. What does it mean by estimating this distribution? It means that we would like to estimate the probabilities, all possible all possible outcomes, and otherwise we said we would like to estimate its histogram or density function, or we would like to estimate, we would like to figure out its distribution, what kind of distribution it is. Okay, so this is our goal. Okay, this is our goal. If this distribution is standard means this is a distribution which can be found in a just statistics textbook. Okay, so then that's good enough. And otherwise if this distribution is not standard, that means it cannot be found in any textbook, then we would write to plot its histogram. Okay, so this is Bayesian estimates. And then to figure out what kind of distribution it is, we are going to compute its posterior density, because once we know its density function, and in many cases we can see what kind of distribution is. So for example, by chance you derive this posterior density, and then it turns out that this is the density function of the theta. So then we are very familiar with this density function, and you know that this is normal density. And then once we have this normal density, and then we can see its mean and variance, then this is Bayesian estimates. Okay, this is Bayesian estimates. Then it's done. Okay, right? Okay, and of course we can derive this posterior density using what? We are going to use Bayes rule. Okay. Okay, let's do this. We are going to derive this posterior density using this Bayes rule. So we just apply the Bayes rule. So probability A given B. So theta is A, Y is B. Okay, and then to compute this, there are two important notes. The first one is between theta and y is non-random at this point. Okay, because y is fixed. Y is the data. Okay, y is the fixed numbers in Excel file. Okay, so y is just numbers. Then what about f of y? Property of y. Okay, this is also number. Of course, we don't know the we don't know the exact value of f of y, right? But what we are sure is that f of y is just number. It must be constant. That means it doesn't change. It doesn't change according to theta. You can put 0.2, 0.3, whatever here, whatever in theta. But f of y will not change. Okay, so because f of y is not a function of theta, this is just constant. Okay, so this constant, this just number. Okay, f of y is just number. Okay, this just constant term. And the other thing is that, okay, let's go back to this normal density. This is normal density. And what about this? The first term, 1 over square root of 2 pi sigma squared. This is a function of theta? No. This density function is function of theta, right? So that if you put different theta, then you will have different density. You will have different density value. But the difference is not caused by this term. This is just constant, and particularly this term is called what? This term is called what? Normalizing constant. The role of this term is just make the integral of density equals 1, right? So once we know this term only, then we are sure that this must be normal density, right? There is no need to know the full functional form, right? So we need to know just kernel. Okay, we don't need to know the specific values of the normalized constant. Once we know this kernel, then we can see what kind of distribution is, right? So we are going to derive the kernel, which is subject to the random variable. Okay. So in this case, we are going to derive the kernel of theta. Okay. Instead, we are going to disregard the constant term. Okay. Okay. This is our goal. And once we derive the kernel, then we will be able to figure out the distribution of the theta. Okay. From its density function. Okay. Okay. So now the first note. Okay. This term is again constant. This is constant. Okay. This is not a function of theta. So that we can say that this posterior density is proportional to this term times f of theta, pi of theta, right? So then what's the name of f of y given theta? What's the name of f of y given theta? We have seen this before, right? What is this? This is what? This is the likelihood, right? Here. This is the likelihood. This is the likelihood, right? This is the likelihood. And what is this? Pi of theta. Pi of theta is called what? Pi of theta is called what? Pi of theta is called what? This is prior. Okay? This is our prior. Okay? And do we have prior? Yes. This is our prior. This is our prior for theta. Okay? And we have the prior density here. Right? So here is pi of theta. And here is f of y given theta. Okay? So then we are going to plug the likelihood in here, and we are going to plug the prior density in here. Okay. Okay. So again, so this is the likelihood, and this is prior density. And here, this term is also what? Just constant. You don't. There's no point to care about this. Okay. So then, posterior density is proportional to proportional to the product of likelihood and prior density. And this is the likelihood, and here is the prior density. And you see that I just disregard this term. So that's why we have here the proportional. And here is theta, and here another theta. Here's 1 minus theta term, and here is another 1 minus theta term, right? Then you see that, then you must be what? Alpha 0 minus alpha 0 plus 2 minus 1. And beta 0 plus 8 minus 1. We can do this. And this is what? This is the kernel of this posterior density, right? And we are very familiar with this form. This is what? This is kernel of what? Kernel of what? Actually, this is kernel of beta distribution, right? Let's compare to this prior density. This is this kernel of the prior density. And this one. They are the same. The only difference is what? Here is alpha 0. And here what? Instead, alpha 0 plus 2. Here, beta 0. Here, beta 0 plus 2. This is the only difference. So then, now we can see that, this is kernel of the beta distribution. Because its density is beta distribution, then its distribution must be beta distribution. And then the parameter must be what? Alpha 0 plus 2. Alpha 0 plus 2 and beta 0 plus 8, right? Then now the parameters are alpha 0 plus 2, beta 0 plus 8. Then its mean will be what? Mean will be what? Alpha 0 plus 2 divided by alpha 0 plus 2 plus beta 0 plus 8. That means alpha 0 plus 2 divided by alpha 0 plus beta 0 plus 10. So this is the posterior. This is posterior mean. Prior mean is what? Prior mean is what? This is prior mean, right? And here is posterior mean. Okay. Then again, this is our prior. According to our prior, alpha 0 and beta 0 are both 5. So then prior mean is 0.5. Roughly, I think the probability ahead is 0.5. Of course, it could be larger or smaller than 0.5. So this is just my best guess. Okay. And theta hat, this M80 estimates, maximum likelihood estimates, is 0.2. So that means, okay, let's go back to the M80. Okay, go back to M80. So how we derive the M80? So we got this number using what? This likelihood. So this is obtained from what? This is obtained from information in data only. There's nothing else. We use only the information in data. We don't use any other information. I mean, we don't use any other prior information. Okay? We don't use any theory, or you don't use any your intuition. Okay? We rely on only the information in the data. And according to the data, the theta is 0.2. This is the best guess implied by the data. Okay? So again here. So according to the data, theta is 0.2. And according to our prior information means that we don't use any data. We use the information before the y is observed. Okay, right? So then according to our prior information, it's 0.5. And once we observe the data, now my best guess is now 0.35. Okay, so this is my guess. This is my estimate before y is observed, and this is estimates implied by only data. this is information contained in the new information, and this is what? This is a combination. This is combination of my prior information and data information. So that's why this is in the middle of in the middle of 0.5 and 0.2, right? So this is combination of the prior information and the information in the data, right? And now suppose you don't have any prior experience about flipping coins, and you know nothing about the coin toss. So you have never heard of coin toss. Actually, you don't know coins. Actually, suppose that. So that means you have no prior information. That means alpha 0 and beta 0 are both 0. We say this is diffuse prior because you don't have any you don't have any bias in the probability of the theta. Okay, so once you have no prior information, then your guess must be dependent on the information in data only and nothing else, right? So then alpha 0 and beta 0 are both 0. Then what? Theta given y, expectation of theta given y, what? 2 over 10, 0.2, right? 0.2, which is the same as the maximum likelihood estimates, right? So that means if you don't have prior information, then your posterior mean should be equal to the maximum likelihood estimate. Okay. Now suppose alpha 0 and beta 0 are both 1,000. It means what? Prior mean is still 0.5, right? But your prior is very strong. Why? Because again, let's go back to here. Okay, your prior mean is still 0.5, but your variance theta will be but smaller or larger than the case that theta is alpha 0 and beta 0 are both alpha 0 and beta 0 are both 5, compared to the case that alpha 0 and beta 0 are both 5. If the alpha 0 and beta 0 are both 1,000, this variance of theta is much smaller. It's very small. The small variance means what? Small variance means what? Your prior is very strong. You believe that theta must be around 0.5. It can't be 0.6, 0.7. It should be very close to 0.5 because your prior density is very tight around 0.5, right? So here again, so now this is 1,000, 1,000, 1,000, right? Then it should be approximately very close to 0.5. So right? So then if your prior is very strong, or you have so much prior information, then even if the data is given, if data is given, then you are not going to change your mind. So some new information will not change your mind, will not change your guess or your expectations, right? So if your prior information is enough or prior is very strong, then data doesn't change your expectation here. And still alpha 0 and beta 0 are both 1,000, but now observation is 1 million. Okay, not 10. Previous it was 10. Now it's 1 million, and 0.2 million observations are 1, and 0.8 million are zeros. Then what happens to this posterior mean? Posterior mean is now 0.2, not 0.5, right? Why? Because alpha 0 and beta 0 are still 1,000, but now you have so much information. So you have so much data compared to these 10 observations. So then if you have sufficient information, sufficient data, then your best guess will convert to the maximum likelihood estimates, right? Okay. So then we cannot simply the data is sufficient or the prior is strong. Strong prior and sufficient data are purely relative term. Okay, they are purely relative. Okay, between prior and the data information. Okay, they are not absolute error. Okay, yeah, I think yeah, we are done today.